Hello class, today I'd like to introduce some of the topics for doing basic simulation analysis in SolidWorks. Let's start by creating a part. Click on New, Part, click OK. We're going to make a very simple part for this exercise. So create a sketch on the right plane, then I'm going to use the center point rectangle to create a 10 by 10 millimeter rectangle. The size is not critical here, so if you are in inches or if you want to use a different size, feel free. Go ahead and accept the sketch, and then use this to create a bar by extruding the sketch to a distance of 40 millimeters. Again, if you want to use different distances here, it's not going to make a big difference for this exercise. So now that I have some rigid body, I can begin a simulation analysis in SolidWorks. Along with the SolidWorks package, there's a default product which is called SimulationXpress. To use this, I can go to the Evaluate tab and then click on the SimulationXpress wizard. This will open up the wizard, which starts with a little promo telling you about SimulationXpress, offering tutorials, as well as the full simulation package that you can purchase in addition to SolidWorks. We actually have the full simulation package as part of the Office edition at FGCU, but for now, let's just take a look at this SimulationXpress wizard. So to start off, let's go ahead and click on Next. You'll notice that this actually opens a new window in what was our model tree, or rather just below it, and this is our SimulationXpress study with the default options. And you'll also note at the bottom here we have a SimulationXpress study tab, as well as the model tab and the motion study tab, which we'll talk about in a future lesson. So make sure you're on the SimulationXpress study tab, and you can actually go through this one by one steps as laid out here in the SimulationXpress wizard. But I'm going to skip a few of these just so I can talk about the details of each of these features. So the first thing we need to do is we actually need to have a material defined for the part. So we can right click and we can apply and edit the material inside the study separately from the material of the part. If the material of the part is already defined, then this will be the default material for the study. So let's go ahead and apply a material to this part. Again, for this study we don't really care too much about the actual material we're using, so go ahead and check whatever your default is. Mine is the alloy steel. So notice it changes the appearance to show that I've applied a material to this. Again, if you had appearance preset for this material or for this part, it wouldn't bother doing that. And the appearance of the material is actually independent of the material you select, so you can have a different appearance rather than the mechanical properties of the material. So now that that's done, you can see there's a little check mark next to it, and it actually shows us as a check mark inside the wizard as well. The next thing I'm going to do is I'm going to go down this tree and I'm just going to apply a fixture to this part. Now, because this is the SimulationXpress wizard, we only have one option, which is to fix the geometry of one portion of this part. When we talk about the simulation toolkit and the full version of the simulation analysis inside SolidWorks, we'll go over some more of the options available for fixtures in detail. So for now, let's select Fix Geometry, and I'm just going to fix the left side of this bar. Select that face and then click on the green check mark to accept that selection. You notice it applies these green arrows which tell me that that side has been fixed, or the boundary condition for when it solves this is going to set the displacement of all the points on this face equal to 0. More about that in a second. The next thing we need to do here is to add a load to this body, so that way some force is being applied. So if you right click on external loads, I can apply a force to any portion of this body. I'm going to go ahead and apply a normal force to the top of this bar, because that's probably the simplest load we can apply. And just to give it some significant value, I'm going to set it to 1,000 newtons, or 1 kilonewton. Again, we're not really testing for failure here, we just want to see how this works, so the values are not that important. So go ahead and accept that load. Now we have both the material, the fixture, and the load defined. We need to run the simulation. Now, because this is the SimulationXpress, we don't have a separate tool across the top here, so let's go back to our SimulationXpress wizard. So I'm going to go to the Run tab, and I'm going to click on Run Simulation. This actually does a few things all at once. I'm going to stop the animation so it stops wobbling on me. It actually creates the mesh for the object, which is what it needs to do the calculations, and then runs the simulation itself. First, let's take a look at the mesh. So I've come back to the SimulationXpress model tree, or the simulation study tree. I can right click on the mesh and I can say show mesh. And this allows me to see what the actual mesh for this object looks like. Now the mesh is what is being used to perform the calculations on this analysis. This is what we call a finite element analysis. So each of these intersections of those lines is actually a node of the analysis, and that's where all the calculations are being done. And then the size of these triangles, or these pyramids rather, if you look at them in 3D, determines the properties or the relationships between each nodes. I'm going to go over to the Prezi real quick just to show you the overview of that. So here you can see this is a similar study that I've done previously, and we've fixed the left side, which creates one boundary condition. We've applied the load to the right side, which creates another boundary condition. And then what this is doing is for each of these nodes, it's going to calculate the deformation between the nodes as a function of the properties of the element. So the element is the area created by the boundaries of the nodes, and then the calculation is going to calculate a displacement between each node as a function of the boundary conditions, mainly the fixed condition and the load condition. So it'll do that for every node inside the simulation. The more nodes you have, the smaller your elements, so you get more accuracy. But again, it takes more time to calculate because it does have to do a calculation for each one of these nodes. So you imagine if you had a very large part with very small elements, you'd have a very, very large number of nodes, and therefore it would take a long time for the simulation to run. It's part of the reason why we're doing such a simple analysis for this example. So now we know a little bit about how the finite element analysis works. Let's look at the results. So now we have the results here. We can open up the results tab, and I can look at any of the different factors here. So I have the stress. I can right click and show the stress, and this actually shows me the stress distribution. And I can actually come over here back to the right, and I can play the animation associated with that too. Let me stop that. Try from over here. Show, animate. So we can actually show this as the stress is varied. So as the stress increases, we can see how it distributes here. We can change the speed of this playback by changing this slider. And if we had the full version open, we can change the number of frames as well to make this a smoother transition at the slower speeds. So we leave the animation. We see the distribution of stress that we expect. At the base of the material, we have a fairly large concentration of stress at the top and the bottom. So if you remember your mechanics of materials, this is largely a bending moment with a relatively small shear load. So the stresses are highest at the base and at the maximum or the furthest distance from the neutral axis. The neutral axis is shown here in blue, the area of the lowest stress. And the heat gauge over here on the right tells us the relationship between the color and the stress at any given point. We can also get some details out of this if we export the results from the study, and it'll tell us more of the actual maximum stress and things like that, and which is also easier to pull out if we look at the simulation toolkit inside SolidWorks. This does give us a pretty good idea of the stresses and the distribution of stresses inside of a part. We can also show the displacement. This is the linear displacement, so the total change in distance of the part before and after the study was run. So it doesn't care about any angular deformation. This is pure linear displacement. And again, we're measuring this in millimeters because the system we've defined. And you'll notice here that even the maximum, the displacement is actually only 0.05 or about 0.05 millimeters. So the displacement that it's showing is much exaggerated. Again, we can animate this as well, and we can see it. And if we were in the full wizard, we'd actually change the defaults of how much this is exaggerating that in the display. So we'll look again at that later. Deformation just shows us the deformation of the part. Again, it has a factor associated with it that makes the deformation scale larger. We can see this up here at the top. So any linear deformation displayed on this picture is actually 83.3 times the actual deformation. So it seems like a large deformation, but it's actually fairly small. And then finally, we can see the factor of safety, and this just shows us any areas where the factor of safety has been exceeded. Now we can go through and we can rerun this by changing any of these properties or changing the part. We obviously have a part that's much, much stronger than it needs to be, so we can start by making the part smaller. I'm going to go into my part model tree, select my sketch, and I'm going to make this part thin. I'm going to make it weaker. So I'm going to set the thickness of this, rather than 10 millimeters, I'm going to set it to 1 millimeter. and then I'm going to rerun the study. So I'm going to go over here to the SimulationXpress wizard, click on Run, and then click on Run Simulation. Oh, looks like I forgot to rebuild the part first. Let's try that again. So here you need to click on the Rebuild button to rebuild the part after you make those changes. Now I have the second simulation study. You notice the deformation looks the same, but look at my deformation scale now. It was 83 before, and now it's 0.09. So it's actually showing much less deformation than there actually is there. So if we look at the stress in this case, I can show the results of the stress study. Oh, let me stop the animation first. So if I right click on the stress and click show, you can see we have a von Mises stress now of 1.086 times 10 to the, or e to the 10th, or times 10 to the 10, which is much, much higher than it was previously. And if you look at our factor of safety diagram, we can see that this part has failed drastically. So anything shown in red, the stress was higher than the yield stress of the material, or the factor of safety was less than 1. So if we want to ask ourselves what is the thinnest that this part can be while still holding the load that we've applied, we can actually run an optimization inside SolidWorks. So now let's take a look at the Optimize tab. So go and click on number 6 for Optimize. I want to ask you, would you like to optimize your model? Make sure Yes is selected, and then click on Next. So now it's going to select me to select a parameter for optimization. I want to use the height of my bar from the dimensions, so I'm going to click on that dimension from my sketch. So it says D1 from sketch 1, and the initial value is 1. So I'm going to go ahead and click OK. You notice that it's entered in here. I can set the range for this value. So I'm going to set the range. I already know this is failing at 1, so I'm going to set the range for the minimum at 1. And then I know the maximum that was okay was at 10, so I'll set the max at 10. And now what I want to do is my constraints, I want to make this as thin as possible while not failing. So I'm going to say my constraint is going to be factor of safety. I'm going to set the minimum factor of safety to 1. And then for my goals, I'm going to minimize mass. This is the only goal it really gives you for the SimulationXpress, but this is a very common design goal. So now I can rerun the optimization. A quick word of warning before you run these optimizations. This can take a lot of time because what it's going to do is it's going to run the simulation, change the variables you've selected, run it again, change the variables you've selected, run it again, and so on and so forth. And what it's going to try and do is it's kind of trying to predict what value among your variables will achieve the constraints at the lowest minimized mass. So you want to kind of be smart about what you pick for the ranges here. If you pick ranges that are too large, it might not converge on a reasonable solution. So let's go ahead and run this and see what we get. So here it's running one scenario where it's failed. Now it's running the maximum scenario where it was successful. Now it's trying to figure out what range is best. So here it's run through several optimizations and it's found the optimal height to be 5.5 millimeters. And the factor of safety that it came out with was 1.55555. Now I can run the simulation again if I want to try and get more accurate than that. So I can actually get this value significantly lower, right? So now if I want to get more accurate, I should change the range of these values. So before I did from 1 to 10, let's say if we do from 4, and we know that 5.55 was successful, so let's do 5.5. Or sorry, 5.5 was successful, let's do 5.5. So now we have a much narrower range of values. So let's go ahead and rerun that optimization. So it's going to run through 5 scenarios, again, testing the minimum, the maximum conditions, and then trying to figure out which the best condition is by running an iterative process. So here now we've got to 4.75. Again, we're closer, still not quite where we're at to be. Maybe we can lower that even more. Again, this is an iterative process, so we could do this as many times as we wanted until we got to where we were happy with the design. So again, let's set the match to 4.75. We know that's going to be successful. We'll set the minimum to 3. We'll try it again. And this will be the last time we bother going through this. So here we've got 4.24, and we're very, very close to our factor of safety. So that's what we could consider a successful design. Obviously, this is not the ideal design for this. We could make some kind of I-beam or something like that, which would further minimize the mass. And it's important to consider the fact that we have only one variable that we're optimizing here. We could add additional variables, and we can, for running the full simulation tool, we could actually change some of the properties of this optimization as far as the number of times it runs before it comes to a solution and those kinds of things. But even here, using the SimulationXpress, we can see some of the power that's available to us through SolidWorks and simulation. I hope you enjoyed this video, and we'll see you in class next week.